Hello, in this video let's discuss some basics of disjoint set union or union find. We have Q queries and there are two types of queries, 1xy and 2xy. If it is 1xy we have to add an edge between x and y, and if it is 2xy we have to find whether x and y belongs to same component or not. That is if they are connected or not. For example 1 1 2, so we are adding edge between 1 2, 1 2 3 and 2 1 3. So now we have to find whether 1 and 3 are same component or not. How can we do this? We can simply do by BFS or DFS. We will start a BFS with 1, and after completing the BFS, we will find whether 3 is listed or not. If it is listed, it means that it belongs to same connected component. If it is 0, it is not listed, so it belongs to different component. And similarly 1 3 6, we have an edge between 3 and 6, and 2 3 7, and there is no 7 in the node, so it is independent, so it is not connected. So it is 1 and it is 0. What will be the time complexity of this? It will be q into n, because for example all the q queries are of type 2xy. So for every node we have to find BFS, and that can be up to O of n. So this is not possible because for example if q is up to 1fi and n is up to 1fi, then we cannot do this. So this is where exactly DSU comes in hand. We are dynamically adding the edges between two nodes, and we have to find whether given nodes are already in same connected component or not. We can't do by BFS or DFS because it will be q into n. So we can use DSU, and let's see how we will use that. So what are the main requirements we want for DSU? We have to find if the given nodes are connected or not. And what is the second one? We have to add edges efficiently, because if we find they are connected in of 1, and if we try to add edge in of n, it is simply useless. And similarly if we want to find O of n with this and O of 1 with this, even this is useless. We have to manage both so that we can complete in less than q into n. How can we say if they are connected? For example, two nodes are given A and B, and how can we say they are not they are connected without BFS or DFS? Now let's think of in terms of connected component. So this is the first component, and this is the other one, and this is the other one. How can I differentiate these two components? If we have a unique value with respect to every component. For example, this is the unique value of this component is 1, this is 2, and this is 3. And now if we have two nodes, and let's say we have one node from this and another node from this, we'll find the unique value of this, which is 2, and we'll find unique value of this, which is 1. So if these both are equal, it means that they are from same components. If they are different, they are from different components. So we can use some unique value for every component, and if the unique values of both are equal, then they are connected, else not. So we'll find unique value of A, and let's assume that function of A returns the unique value of this component, and similarly function of B represents the unique value of that value, that node. And if they are equal, they are in the same component, else not. So this is the first thing we can think to find in O of 1 whether they are connected or not. And coming to add of edge, so how can we add edge now? So now we are trying to add this both. For example, let's say this is the first node and this is the second node, and we have to add edge between these. How can we add edge now? Adding the edge here represents that we have to make unique values of both equal, because we discussed that we are finding the unique values to find whether they are connected. But now in adding edge, we are making both to a same component, so we have to make unique values of both equal. So add edge is simply unique value of A is equal to unique value of B, and find if connected, we have to find unique values of both nodes, and if they are equal, they are in same connected component. And now what can be the unique value of component? So how can you decide this is 1, this is 2, and this is 3? So instead of some hard-coded values or any other logic, we can simply take the ultimate parent of all the nodes in that tree as a unique value. Because let's say this is one connected component and this is the other one. What is the unique value of 1? It is 1. What is the unique value of 2? It is 1. It is 1. It is 1. So for every node in the same connected component, we can take the ultimate parent of the component as a unique value of that component. And this is the second component. It is only 7. So unique value of that is 7. So that is the ultimate parent. So unique value of that can be ultimate parent of that node in the component. So initially parent of every node is that node itself, because initially there are no connected components. So every two unique values must be different. So we can simply maintain the parents of that node itself originally. So parent of 1 is 1, parent of 2 is 2, and so on. And now we have three main functionalities to do. What is the first one? It is add edge. So it is added, and find if connected. and find parent, because in find connected we are finding the unique value, and here unique value is parent, so we want parent, so find the parent. So for we are finding whether they are connected or not. How can you do that? Find parent of a, find parent of b, and if they are equal it is connected, else not. How can we find parent? If the parent of node is equal to node, it means that we have reached the ultimate parent, because let's say 1 2 3, we have merged all these, we have added just between all these, and for one the parent is equal, because initially we made the parent of that node is equal to that node. So if we are at a node where parent of that node is equal to that node itself, it means that it is the ultimate parent. So if parent of node is equal to node, it means we have reached the root node, so return node. Else return find parent of parent node. So the parent of 3 is 2, so return the parent of 3. So by recursion we can find the parent of 3, and now we have completed the 3 functions. Now let's do a dry run. This is the current, this is the tree 1 1 2, so we are adding between 1 and 2, 2 and 3, 3 and 4, 3 and 5, and 4 and 6, and now 2 5 6. So we have to find whether 5 and 6 are in same connected component or not. So let's start the traversal 5. For 5, what are the nodes that we have to traverse? So for 5 we have to travel to 3 to find what is the parent. For 3 we have to go to 2, and for 2 we have to find for 1, and ultimately when we reach 1, this is the ultimate parent, so we will return 1. So for 5, to get the ultimate parent node which is 1, we have to travel all the nodes from 1 to 5, and similarly for 6 we have to ask what is the ultimate parent of 4, our ultimate parent for 3 and 2 and 1, and at 1 we can return that one. So for at least, so for a single 2xy we are traversing all the nodes in the given one, which is very bad. So this is often, so we cannot do this, because for every one we have to traverse all the nodes, so often is not possible. So how can we optimize this? Once we find a parent of a node, it will not change, because we have 1 and 2, and is there a possibility in this case the parent of 2 will be other? So if a parent of node is found now, it will be same for the rest of the queries as well. So instead of trying to find the ultimate parent of node every time, we can simply store in the parent of node which is the ultimate parent of that one. So for example, we are trying to find the ultimate parent of 5. So ultimate parent of 5 will be ultimate parent of 3, it will be ultimate parent of 2, it will be ultimate parent of 1, which will be 1. So instead of doing this blindly, and for example if the next query it is 2 3 4, and now similarly for 3 we have to find ultimate parent of 2, ultimate parent of 1. So we can see that there are many duplicate and waste iterations. So instead of doing that, we can simply store parent of node which represents the ultimate parent of that node. So in this case, while traveling for 5 to 1, we will store the ultimate parent of 3 is equal to 1, and we can find the ultimate parent of all the nodes from the root to that node. So for a given vertex, we are calculating parent from all the nodes from root to node in a single iteration itself. So even in the next queries, if we get 2 3 2 or 1, we can we have already computed that, so we can simply return that in of 1. So find parent of node. So if that node is equal to parent, return node. Else return parent of node is equal to find parent. So why we are storing? Because we can simply pre-compute. For example, we have 1 2 3 4, and now we want to find ultimate parent of 4. We no need to find ultimate parent of 3 and 2 for now, but we may require this later. So for by finding the ultimate parent of 4, we can store ultimate parent of 3 and 2 and 1 as well. So in this way we can find for other queries in of 1. So parent of node equal to find parent of node. Now it will be of login, which is very far less than of n. And now what we have done, so while finding for 5, we have found the parent of 2 is equal to 1, we have found parent of 3 is equal to 1, and parent of 5 is equal to 1. So simply we are trying to break this one like 2 3 5, because initially 2 3 5 is cubed, and we found the parent of 2 is equal to 1, so ultimate parent is 1. So it is simply parent of 2 is equal to 1, because parent of 2 is equal to 1, I have stored that parent of 2 is equal to 1. It means that ultimate parent of 2 is equal to 1. So this represents that there is direct edge between 2 and 1. And similarly we have stored for parent 3 as well in the same recursion function. So parent of 3 is equal to also 1, and this also represents that there is direct edge between 1 and 3, and similarly 1 and 5. So we have compressed the whole path to single leaf vertices. So this is very great, right? Because for finding the answer for single node, we found the answers for every node, and we have compressed the path as well. So We found how to find the parent of node in of login, which is the ultimate optimization. And now the two functions remaining are find whether they are connected or not and add edge between two nodes. Can we combine these both functions to a single one? Now we can try to create a new function int merge two nodes. So we are finding the parent of both nodes, and if parents are equal we are returning one. It means that we are finding whether they are connected or not, which is this exactly this function. And if they are not connected, so we are making parent of parent b is equal to parent a. So we have two different components, and this is the ultimate parent of this component, which is the ultimate parent of b, and the ultimate parent of this component will be parent of a. And now when we are trying to add edge between these both, how can we add? So we discussed that we are going to make unique values of these both equal. So we can simply make parent of parent b is equal to parent a, or parent of parent a is equal to parent b. Now let's assume that we are trying to make parent of parent b is equal to parent a. So and we are returning 0. It means that they are not connected, and now we are connecting. So by single function, if the requirement is connected, we are getting the boolean value which is 0 or 1. And similarly, if they are not connected, we are adding edges. So by this one, we are going to achieve this both. Now let's discuss the example. We have 1 to 3, a single component, and we have component 4 to 9, which is Q3. And now we got a query to merge 3 and 8. How can we merge this? So we will find the ultimate parent of 3, which is 1, and ultimate parent of 8 is equal to 4. So now indirectly we are merging 1 and 4 together. So how can we merge 1 and 4? There are two ways. We can make parent of 4 is equal to 1, and we can make parent of 1 is equal to 4. So which is better? So if we observe more, surely the second one is better, because the height of the tree is becoming more skewed in the first case, because the height of tree originally here it is 1, and the height of tree here is equal to 5. But now if you are trying to make parent of 4 is equal to parent 1, the height is 6. And now if you are trying to make parent of 1 is equal to 4, the height is 5 itself. So we are making more skewed by adding the ultimate parent of 1 with a higher rank or size or height. So what I'm saying is, for example, we have these two, 1 and 4. So which is better to make parent of 4 is equal to 1 or parent of 1 is equal to 4? It is better to add with the less height to the higher one, so that we can maintain the balance between the new tree and the old tree. So better to make height of size is balanced. So we can see that the height of this is more than this one. So it is better to make the edge connection such that, let's say this is the parent A and this is parent B. So when it is beneficial to make parent of parent A is equal to B, it is better when the size of B is equal to high. So if of B is equal to more, then it is better to add edge parent of parent is equal to B, so that we can maintain the balanced T. So we are finding the parents of both nodes. If the both parents are equal, we are returning 1, saying that they are connected. And if the size of parent A is greater than equal to size B, so this is, let's say this is parent of A and this is parent of B. So which is better? So it is better to make this one, so that we can maintain the balance of height. So if the size of parent A is higher, we are making parent of parent B equal to parent A. So we are making parent of parent B equal to parent A, and the new size of PA will be the whole one, because we are adding the PB to this one. So the size of this will be increased by size of original B. So size of parent A plus equal to size of B, and similarly the other case. And finally returning 0. It means that there is no connection till now, and we are adding the edges. So in this way we are trying to balance the height as well. So this is nothing but union by size, because union is nothing but merge, and union by size because we are taking the size. We can take with respect to height as well, but size is more simple. So we are going to take size vector as well, and while merging, we will check whether size of which parent is more, and based on that we are going to make the new parent. 90% of the cases this one also will pass. Only for few cases where there are heavy finding or heavy computation, then we want union by size. So in this way we can simply do the merging in of login. So the time complexity of both union by size and path compression of flow of login, we can simply use this in queries, and we can get time complexity of q into row of login, and which is the most optimal. And let's discuss a small mistake that we can possibly do. For example, we have completed processing the DSU, and finally we have to find the parent of node X. So how can we find it? So is it simply parent of X? It can be parent of X, but there can be a case where parent of X is not the updated value. So every time we are going to use the parent of a node, it is simply better to use find of X always, because it is law, or it is because this is law of log n as discussed. So instead of trying to use parent of X, because that can be not updated as well, but find of X will update the present values for sure. So for example, we have three queries: find the parent of 2, find the parent of 3, and find parent of 3. And now we are encountering 2 for first time. So we can find the answer by find function of 2. And coming to next one, 3 is also found. But there may be a possibility that find the parent of 3 is not updated properly. So it is surely better to make find of 3 again. And now this is already computed before in the before query. So now the parent of 3 will be correct, and we can simply use parent of 3. So there may be a possibility where the parent is not correctly updated. So we can use find of X because it is law of login. So in this way we can try to find the latest ultimate parent for every node. And coming to next one, we can create a class or no need to create a class, and that depends on the platform or retrieve. So we discussed how to write the functions union and find parent. So we can try to modify those with respect to the conditions. Let's discuss the code. So it is simply parent and size. We are making global values because I am not making class here. So it is better to maintain global vectors. And now we are inputting n and q. And initially we are making parent of every node is equal to itself. So parent of I is equal to I. And now we are traversing the q queries, inputting p, u, and v. And if it is 1, we are going to merge those both. And if it is 2, it means that we have to print whether they are connected or not. So now coming to find, we are finding if node is equal to ultimate parent if yes return this node, else store the value of parent of node which is equal to find parent of node. And coming to merge, we are finding the parent of f and parent of s, and if they're equal return 1 because they are already connected. If not, we are going to merge based on the sizes of both, and return 0, they are not connected originally. So in this way we can try to find the dynamic. So this is mostly used for we want whether two nodes are connected or not when we are going to add edges dynamically. Let's discuss next problems in next videos. Like and subscribe for more content.